there, ladies and gentlemen. This is Mr. Workman. I'm going to take you through your Chemistry of Water screencast session 3 here. I'm going to reiterate to you a little bit about what solutions are, and I'm going to talk to you about some very special solutions that can produce acids and bases. And of course, we're going to talk about the pH scale, which is a scale that measures the relative acidity or basicity of particular types of solutions. So let's get right to it here. I know this is a little bit of a review if you've seen the previous screencast, but let's just make sure we know exactly what we're talking about here. A solution, of course, is a mixture of a solute and a solvent, and these things are not chemically combined, they're just mixed together. So for example, if you're making something called a salt water solution, you're going to mix together salt and water. Now, in this particular circumstance, the solute would be the solid salt, the solvent is the water, and these are your definitions for what a solute and what a solvent is. But another thing that you can think about is that in general, the solute is the lower proportion of the mixture. It's not as much, there isn't as much solute as there is solvent. Now, here's the thing, when you're making a solution, the only way you can really make a solution, the only way you can get water to mix with anything is if that substance is hydrophilic. Materials that are hydrophilic are things like most ionic compounds that can dissolve, covalent molecules, covalently bonded atoms that make molecules that have some polar covalent bonds in them. They'll be hydrophilic. And examples of materials like this would be any type of salt, not just sodium chloride. There's other types of salt like copper sulfate or magnesium bromide. These are different types of salts. Salts can dissolve in water. They're hydrophilic, and so too can sugars or proteins. Hydrophobic materials, on the other hand, are materials that are literally, it says water afraid. Hydrophobia is water fear. Materials that won't interact with water, things like oils or waxes or lipids. And this is generally due to their propensity of carbon to carbon or carbon-hydrogen bonds, which are nonpolar covalent bonds. Let's take a look here at what a dissociating set of ions really means here to make a salt dissolve. So let's say, for example, we've got some water, that would be our solvent, and we put some type of ionic salt in that water. Because of water's polarity, that is its sort of negative side and its sort of positive side, which are respectively the oxygen and the hydrogen sides of the molecule, water molecules can shroud ions so that they can no longer find one another and bond ionically. This is the case here, where you can see that the oxygen side of water molecules are oriented toward and shrouding a positive ion. And over here you see the hydrogen, which is the positive side of water molecules, or the slightly positive side of water molecules, are shrouding a negative ion. Now, let's say, for example, we've got a particular example of an ionic salt, so sodium chloride. That's table salt. That's the ionic compound that most of us are familiar with. Literally what happens when you put salt in water is that the sodium and the chloride ions dissociate. They are no longer associated. They fall apart. And again, the positive sodium ion would be shrouded by the oxygen or the slightly negative side of water molecules, and the reverse for the chloride ions. And what happens is that they can't find one another. The sodium and the chloride ions can't find one another as long as there is enough water molecules shrouding them, making these what are called hydration shells around these ions, so that they can't bond in an ionic crystal any longer. I have a little movie here that sort of depicts, well, it doesn't sort of, it actually depicts the sodium and the chloride ion dissociation. It's important that you understand, too, that we're not just dealing with solutions of salts dissolved in water. There's other types of solutions that can occur. And it's important to know that water itself can dissociate. Now that's kind of weird, but it actually can happen. So here's a water molecule, and what can happen and does happen is that one free proton, which is essentially a hydrogen ion, can break away from the remaining part of the water molecule. And this is what I would call a hydrogen ion. It's really just a proton. And this is something I'd call a hydroxide or a hydroxyl, depending on the context that you're using these words in. And their presence and their relative abundance is really important for living systems, because it is the relative abundance levels of hydrogen ions and hydroxide ions that's going to determine the acidity or the basicity of a solution. In general, if I put something into water that can dissociate and add more hydrogen ions, that's going to make a solution more acidic. This is a hydrogen chloride situation. If you put some of that stuff in water, the hydrogen can dissociate from the chloride, just like the table salt did, the sodium dissociating from the chloride in the previous little movie clip you saw. And what happens effectively is you increase the amount of free protons or free hydrogen ions in solution. And when you increase the amount of hydrogen ions in solution, that makes the pH number go down, and it makes a solution more acidic. In contrast, if you increase the number of hydroxide ions, which is this OH situation, if you put more of those into a solution, that makes the pH number go up. That makes a solution more basic. So sodium hydroxide, just like sodium chloride, can dissociate into sodium and hydroxide ions in the same way that water pulls apart sodium chloride. And the hydroxide is what makes this particular solution more basic. You can calculate the pH of a solution by using a function on your calculator that's called the log button. And all you really need to do is type the negative button, log, and then you enter what's called the molar concentration of either your hydrogen ions, or if you want to, you can calculate pOH by entering the molar concentration of your hydroxide ions. Now, molar concentration is something that I'm not going to get into a lot here, but what it really means is moles per liter. And a mole is a chemistry counting unit, kind of like the word dozen is an everyday counting unit, and it's taken to mean the number 12. Well, moles in chemistry means a huge number, which is 6.02 times 10 to the 23rd, and that's a really big number. If I had a mole of marshmallows, it would cover the United States about 2 miles thick. It's a really, really big number. Anyway, if you put in 1 mole of hydrogen ions per liter, you define that as pH 0. The pH scale is this. So here's this molar concentration thing of hydrogen, and if you have a concentration of 1 mole per liter, which is 10 to the 0, that is defined as pH 0. And the pOH is going to be an inverse relationship with the pH. So what will always happen is that your pH plus your pOH will add up to 14. It's important that you know that pH of 7, which is a neutral solution, what that really means is you have an equal number of hydrogen and hydroxide ions. And if you have an acid, what that means is you have more hydrogen ions than you do hydroxide. And if you have a base, it means that you have more hydroxide than you do hydrogens. So what does that really mean? Well, this is a pH scale that reflects the logarithmic scale of hydrogen versus hydroxide. And it's important that you know that every one number that goes up on the pH scale, really what's happening is the relative concentration of hydrogen ions is decreasing by a factor of 10. So you can look at it that a pH 2 acid is 100 times stronger than a pH 0. A pH 0 is 100 times more acidic than a pH 2. A pH 0 is 1,000 times more acidic than a pH 3, and so on. It's important that the hydrogen and hydroxide ions are balanced in living systems, because particular pHs are required to supply or support living operations and living processes. Our blood is slightly basic, and it needs to remain so, otherwise particular critical functions can occur to keep us alive. Different materials have different pHs. In general, acidic materials taste sour, and basic materials taste bitter. High pH material can feel slippery. This is why soap is slippery. It's also important to note that life reactions can cause pH changes, and so there's a need for cells to be able to regulate their pH. And the way that they regulate their pH is using something that's called buffers. Buffers are chemicals that can either donate more hydrogen ions to solution, or accept, that is, grab or trap hydrogen ions out of solution to keep the pH of a particular solution within a designated range. As you see here, this material called H2CO3, that's hydrogen carbonate, can either break apart and release more hydrogen ions, or this HCO3 minus could accept more hydrogen ions and turn back into H2CO3 as needed. This reaction can go both ways, which is what's designated there by arrows going in both directions. And our cells have these buffering mechanisms in them so that we can balance the pH of our blood or other bodily fluids as needed to keep our bodies and our cells healthy. So that's really it about solutions again, and how to calculate pH and what pH actually means. Hope you learned something, everybody. Take care.